start now. Hello, everybody. I'm going to introduce myself. I'm Karim Azoum from the French National Competence Center. Welcome to the training on numerical computing with Rust on CPU. This training is co-organized by NCC France and NCC Slovakia. I want to say a special thank to Lucia and Michal and all the team for their support. This training, this 3 half-day training on Rust on CPU is also organized with the participation of GCLab, the National Supercomputing Center of Slovakia, and also Sona Lake. Adrien Graland is the teacher. He is a software developer at IGC a French laboratory attached linked to CNRS and the Paris-Saclay and Paris Cité universities. Something else on Adrien. He was one of the teacher of the Gray Scott School we organized in July 24. We are going to talk about it after, but just to introduce the Gray Scott School. So, as you know, the program is shared into 3 parts. Adrien is going to give you everything as information, but just as a resume, we have 3 parties: sample Rust computation, numerical simulation in Rust, and optimization Rust performance. Just to give you some information, as you know, we have a website dedicated for this training. You have all the information, all the courses, or all the exercise enclosed in containers. You have also in this website all the environment setup. We are going to use the same link of Zoom during the 3 parts. We have also a Discord of the Great Scott School. There is a lot of information. You can have access if needed. We have also a YouTube dedicated for the NCC France with a lot of courses inside if needed. Something else, just to give you some information, because I introduced the Gray Scott School. It was organized by NCC France in 2024 of July. It was 2 weeks HPC summer school, 1 week dedicated to CPU, 1 week to GPU for programming and optimization on heterogeneous architecture. Something really interesting is that this summer school was accessible by 12 satellites in France, but also in other countries, because 4 countries participated in the Great Scott School with 9 teachers. Adrien is one of these 9 teachers. And something really interesting, we trained more than 500 people during this Great Scott School. And in 25, we are going to deploy this Great Scott School in English with European satellite seat. So if interested, just send us a mail. We can give you information. And the training of today focus on CPU and on Rust on CPU was one of the courses deployed during the Gray Scott School. So it is just to understand and to make link about the courses of today and the Gray Scott School. So thank you very much for your attention. Just to give you some information more than 200 we have for this training more than 240 registration. Now, I think online, we are more than 120 people, so it's a very big success. Thank you coming to join us. I'm going to give the floor to Adrien. Just before that, Adrien, you can share your presentation if you want. Just going to give some more information. On Zoom, you have
Yes.
you have a chat. You can use the chat only for general information. If you have question and you need answer, uh, especially for Adrien, please, you have a Q&A topic for that. So please use it for the question. Thank you very much and have a really good training. Thank you.
So hopefully you can see those slides. I will not ask all of you to reply to this, obviously.
Yes, yes,
So
of course.
welcome to this training. As an introduction, I wanted first to give a bit of motivation for why you might want to use Rust for numerical computing and how it differs from its competition. So let's start by asking the question, what would be my ideal compute language? So, we can do numerical computation with many different tools from Excel to Python. First of all, I like general purpose tools. I don't like to use one different tool for each thing I do. That unfortunately eliminates quite a few tools which are specific to some hardware or some kind of computation. Then I also like, because I'm kind of a performance engineering expert, to have an environment where it's easy to get to the peak machine performance. And this unfortunately precludes the functional languages and object-oriented languages. It's also quite hard to get Python to a decent speed often. And even on Julia, it's a bit hard. And then the third characteristic, which I like in the languages that I use, is that I want them to be well equipped for larger projects, because I have often observed that many of my large software projects started as small ones, and it's really hard to tell in advance, is this going to be big or not? So I like if right from the start, I can use a language where I know that if I need things like encapsulation, generics, polymorphism, code generation, hierarchized API, I can have it. And of the languages I know of, at least when I've set the three criteria, I don't have much of a choice left. So C++ and Rust, which I would spend the rest of this talk comparing, have many ideas in common. The normal way to use them is ahead of time compilation. You start from the source code, you produce a binary, and then you can run this binary on the machine, and there is no compilation happening at the runtime stage. They don't force the use of garbage collection. They have a relatively sophisticated type system with quite strict typing rules. They give you quite a bit of control and low-level machine operation during program execution. They have quite a bit of metaprogramming capabilities for controlling, for generating code during compilation and things like that. And they provide a rich abstraction vocabulary, including so-called zero-cost abstraction, which you don't pay for if you don't use them. And if you need to use them, they should be as fast as the code you would have written yourself for the same purpose. The price to pay for all of these nice properties is that both languages are quite difficult to learn. It takes a while to master. So since so many of these things are common between C++ and Rust, what does Rust do differently? Well, one thing you must have heard of if you've ever studied a bit the question of, what is this Rust thing and what does it do on the internet, is in C++ we have a bit of an undefined behavior problem. So what is that? Undefined behavior in a programming language is special patterns of code execution that in modern days, the compiler optimizer assumes cannot happen. By that, I mean that when your program goes from the source to the binary, some optimization steps will be run. And this optimization step will make the mathematical assumption that there is no undefined behavior. So if there is undefined behavior, they will produce wrong results and your program will behave in a completely unpredictable way. And unfortunately, in C and C++, we have many of these. They go from simple arithmetic, use of arrays, pointers, references, initialized memory, infinite loops, multi-threading. Basically, there are so many cases of undefined behavior in the C++ specification that it's unavoidable that sooner or later in your real-world code, you will face some of it. One very well-known consequence of this is security issues. Many large C and C++ projects have been recently studying the proportion of vulnerabilities that is caused by memory safety issues, that is to say, null pointers, dangling pointers, buffer overflow, that sort of stuff. And basically, we are almost always around 2/3 of the vulnerabilities caused by this sort of issues, which are just, again, one kind of undefined behavior, even if it's quite a broad one. To that, the answer of Rust is to make a safety pledge. That is to say, outside of unsafe blocks, the contract that the Rust compiler sets up is to prove the absence of undefined behavior, which is called undefined behavior safety. More precisely, the compiler will prove 3 kinds of safeties in theoretical programming jargon. Type safety, which is to say that the values you are manipulating honor the invariants set out by the types. Like, for example, if you manipulate a string in Rust, strings are UTF-8, so you cannot have a string that contains bytes which are not legal in an UTF-8 sequence. Second, we have memory safety, which means that any reference you hold to memory have to point to memory that is valid, that contains a valid value of the type, that is initialized. And third, we have thread safety, which means that anytime in a multi-threaded program, you have one thread writing to some shared data structure, you have a guarantee that there will be no other threads concurrently writing or reading to this data. That's a good compromise in practice. We do need to have some sort of unsafe blocks escape hatch, because proving all of these things at compile time may be impossible in some contexts. For example, if you're doing embedded programming or operating system development, you cannot prove sometimes that nothing else holds a reference to some piece of memory. And second, you may say, okay, I cannot prove it at compile time, but maybe I can check at runtime like Java does, for example. And yes, you can. But if you do it too often, at some point, it can become expensive. And that's the second use of unsafe in Rust. Sometimes we need to use unsafe code which can have undefined behavior for performance in order to eliminate a runtime check that has become too expensive. The good news, however, is that these two are relatively edge cases in practice. We can do most of our work without ever using unsafe code. This means that ultimately in a larger Rust program, the use of unsafe is normally very localized on a few modules or lines of code in the program. And it's much easier to audit unsafe Rust code than C++ code as a result. The second issue with C++ is that its type system has over time accumulated a number of weaknesses. I've talked earlier about undefined behavior, but there's also quite a bit of C++ behavior that is perfectly defined according to the specification, but makes no sense to the C++ practitioner. And these usually come from interactions between the many different polymorphism mechanisms available in C++, which include implicit conversion, including those that you declare without thinking about it when you fail to declare a constructor as explicit. It includes also function overloading. That's another way to have multiple functions of the same name that do different things. Default arguments can lead to the same outcome. Templates are also a way to have code that behaves on different types in a possibly different manner. Specialization is all about doing this voluntarily. If you use the more object-oriented side of C++, virtual methods of inheritance are yet another way. And each of these in isolation is relatively easy to understand, but as soon as you use combinations of these, it becomes quite difficult. Templates in particular, I would like to single out because they are especially hard on the implementation side to write templated code. And the reason is that there is a really minimal type checking of the code inside of a template as long as it's not been instantiated. In practice, this feels a lot like writing in a language where everything is checked as runtime, like Python and JavaScript. The difference is that instead of errors happening at runtime, they happen at instantiation time. But since you cannot instantiate templates for all possible types in your test, the end result is effectively the same. You have some results that will only have, you have some errors that only your end users will encounter that you cannot find ahead of time. To make this more concrete, let's look at a simple C++ program. So imagine I'm using some templated function from a third-party library that computes the median of a vector of floating points inputs, float, double. And in my code, I just write stdc out. I pipe in the median of some small vector. I write an end of line and flush. Should work, right? Well, until it doesn't. The compiler is clearly unhappy with this code and spams us with a very, very long error message featuring many comments about some use of operator arrow arrow, but it's not the operator arrow arrow that we are using in our code actually, as we will soon figure out. It's inside of the implementation. So okay, let's look at the implementation. Can we find what in here might be causing the problem? Well, there's not only one problem here, unfortunately. First of all, you may have heard about the concepts introduced by C++20. And earlier when I said that templates are hard to write, you may have thought, okay, yeah, but these days we have concepts, they should fix that, right? Well, until they don't. By design, C++ concepts only work as intended if they are manually kept in sync with the underlying implementation code. Here they are not, because I am actually trying to print out the value of an std vector using the IO streams, and that's not something I can do. But the compiler will not find out until instantiation. Speaking of which, it's actually quite convenient during debugging to be able to just see what's inside of your vector. It would be nice if we had an alternative to see out for that. We don't. Also, this code has some undefined behavior issues. Like in the case where the size of the input is even, the way I compute the median is by taking the values on two sides of the midpoint and computing their mean. But that doesn't work in case the input vector is empty, because then I'm accessing value number 0, which doesn't exist, and value number 1, which doesn't exist either. Furthermore, here we have on the right an instance of something that is not a performance problem in this particular code, but very often becomes a performance problem in other code. Is that I mindlessly used a floating point literal to compute this mean. And unfortunately, in C++ and C, floating point literals are typed. They have type double if you don't put an F at the end, which means that here we get a round trip where the sum of the two sides of the midpoints gets converted to double precision, then a division occurs, and then we convert back to float a single precision floating point in order to return the final value. This sort of thing can easily cause problem in larger loops or code bases. Finally, we are calling the standard sort function on our vector in order to compute a vector of sorted element that's a part of an easy median algorithm. The problem is that, unfortunately, when you do that with floating point data, you will get wrong results if there is any instance of the spatial nan floating point value in the input, because nan is not ordered. Fortunately, in this case, the standard library defines that you get a wrong result in this case. Unfortunately, a study found that many third-party sorting functions that you may want to use because they are faster than the standard one are not so careful and will just exhibit undefined behavior in this case. My point is, I've been writing C++ code for something like 20 years now. And even after all this time, the first code I write to solve any particular problem remains full of these little issues. They are not big issues, but there are many of them. And only a tiny fraction of these issues is actually detected by the usual compiler warnings. It takes me hours of proofreading, testing, and so on. Lots of cleverness, thinking about unusual test inputs to finally get a correct result out of my programs for all possible inputs. The answer of Rust to this is to have a stronger type system that prevents more typing errors. By that, I mean that Rust really, unlike C++, has one main polymorphism mechanism, which is constraint generics. The way it works is that any type can implement something called a trait. Traits represent many things. They can be the ability to convert a value of some type to text, overload of the arithmetic operator, comparison, and so on. And on its side, generic code that wants to work for any type must specify what traits it needs from the input types in its external API, like C++20 concepts. Unlike C++20 concepts, however, if your generic code then proceeds to use anything other than the traits it has asked for, you will get a compilation error, which does not occur at instantiation time, but just, by virtue of the compiler checking the definition of the generic code. And that's an extreme convenience. As a consequence of having less polymorphism mechanisms, Rust is a lot more predictable than C++. It's a lot easier, before compiling or running your code to get a picture in your mind of what's going to happen, because there are not anymore any interactions between implicit conversions, overloading, templates, virtual method, etc. Your generic code will fail early on, right at declaration time without needing any instantiation. And it will fail with a clear error message, either on the definition side or on the use side if you try to pass a type that does not implement the right traits. You will not get errors deep inside of the implementation as happens in C++. To showcase this, let me translate the code I showed earlier to Rust. We will get this time 3 different compiler errors. The first one tells us that, yes, in Rust, we cannot directly display vector of t either. However, the new things in Rust with respect to C++ is that we get this error message even if the generic code has not been instantiated. Just declaring it is enough for the compiler to see the problem. Furthermore, unlike what happens in C++, the compiler actually suggests an alternative to the standard text display method, which is the debug display method, which is designed for debugging outputs. And we can produce debugging output in Rust out of pretty much every type, including vectors. Second, the compiler complains that we are not allowed to sort floating point data because floating point types allow for the nan value, which is not ordered, and thus, sorting unordered data does not make sense. If we know that we will not get nan in our inputs, we have then various ways to assert the absence of these in our code. Finally, and this is, I will leave you to decide whether this is a good thing or not. The compiler will also complain about the part where we divide our sum of midpoints by 2. So here the error is a bit harder to understand, but basically the idea is that in Rust, floating point literals do not have a type. They are not double precision, they are not single precision. They will adapt to the context in which you are using them. And here, the issue is that or untyped floating point literals do not have an implicit conversion to an arbitrary type, and they do not have a division operator with arbitrary types. So basically, when the compiler sees this, divided by 2, it has no idea what to do, right? It only knows how to divide values of type t with one another, but it cannot turn the 2.0 into a value of type t, so it's stuck. And then after that, you get some extra explanations linked at the end. I would like to point out that unlike the C++ compiler, the Rust compiler found most errors in the code, but there is still one error that has not been detected. Since our Rust version is a literal translation of the C++ version, it's still incorrect if the input vector is empty. The difference here is that in C++, as I mentioned earlier, accessing a vector out of bound results in undefined behavior. Whereas in Rust, what will happen instead is that the invalid access will be detected at runtime and lead to a deterministic program crash called a panic, which is, we get to that later, but a bit similar to a C++ exception. Now, we may ask, is this actually a good way to handle this error? And I would argue that here, it depends. We can consider this to be a good error handling scheme if we consider that sending an empty vector to something that computes a median is a user error, something that the user should never do. If, however, we make this decision as the implementer, we should set it in stone by spelling it out explicitly in our documentation, saying you should not use this function with empty inputs because it makes no sense. If we do want to account for the possibility of empty inputs, then the right thing to do instead is to return an optional type, which is similar to the std optional of C++ 17, if you know about it. The idea is that this is a type that can either contain a value of a certain type t or no value. And here we would use it to return no value in case the user passes in an empty input because an empty vector has no median element. This leads me to the question of error reporting. So back in the day where I learned C++ or in the early 2000s, the trend was to bet everything related to error handling in C++ on exceptions. But already in that time, there were a few known problems with exceptions, right? Exceptions are quite expensive to throw and to catch, which means that you don't want to call code that throws exceptions in a loop. If you have errors that occur frequently, you will probably want to use a different mechanism. Second, it's actually quite hard to write code that remains correct in the presence of exceptions occurring, because it means that the code can be basically interrupted at any moment on any line of code in the middle of any expression. The whole topic of exception safety has been studied for a long time. People have done many talks about it. We don't know if it will always remain hard. Finally, one last issue with exceptions is in C++, people are discouraged to use exceptions in the destructor of classes because the problem here is that we can get something where you call a destructor because an object goes out of scope. The destructor throws an exception. Then you call the destructors of the variables declared in the initial destructor. They throw exceptions away and so on, and you could get some kind of infinite recursion in that way. And the way C++ resolves this is by just aborting the program if two exceptions occur in a row. So exceptions in destructors are not composable, and then they are discouraged for this reason. So let's say you don't want exceptions. What do? Well, everyone does his own thing. That's a bit of a problem. One typical strategy is to use some special values of your return type. Like, for example, if you return an integer, maybe you will say that the maximal or minimal value of this integer type is not an actual result, but a signal that some error has occurred. A special case of this that is well known to people who have practiced C a bit is to return an integer value whose only purpose is to signal the presence or absence of error. And the problem is that because that's its only purpose, usually people fail to check it. You can say that all of these methods are wrong, and perhaps you're right. but then you will end up using exotic return types like some specific flavor of STD variant that's specific to your individual project. And this makes it a pain to write code that use multiple libraries that each use a slightly different variant of this strategy. And finally, you get the usual issue that the error cases of your function are usually poorly documented. The way Rust attempts to resolve this problem is to have a clearer strategy that encompasses more use cases. In the case of errors that are recoverable, like for example, you tried to open a file and there was no file, or the file is not available for opening, your function can return an enumerated type called results. The idea of the result type is that it can contain either a valid output or an error description. And to get to the output value, assuming it is present, you have no way but to specify in your code how errors are to be handled. And this means that Rust code that uses libraries that use the result type cannot avoid handling errors. It has to do so. So we get much better error handling simply by virtue of this. In the case where your error situation is actually not much of an environmental error, but more of a program bug, like for example, there was an assertion in the code which assumed that something should always be true, like the array indices should be inbound, and actually it's not true here. The index makes no sense. Then we use a different mechanism called panics. This can be configured at compile time to either behave through unwinding, like C++ exceptions, which allows for some program cleanup before the program terminates, or they can abort directly, like C assertions do. And this will allow a reduction in code size and also slightly better compiler optimizations. When we use unwinding panics in Rust, there is an option in the standard library to catch these unwinding panics and resume program execution. However, unlike in C++, this is considered an edge case. It's rare and it's highly discouraged. And the good thing compared to the C++ situation is that there is a strong community consensus around this strategy for error handling. And there is also a strong culture in the Rust community of documenting the error cases of function. So it happens much less often that we get an error in a situation where we did not expect one. Let's cover one last topic, code generation. It's one of these things that has a bit of a bad reputation, but sooner or later, any sufficiently complicated program will need to use it. In C++, one of the most common strategies for code generation is to use so-called template metaprogramming. So in my view, this is basically a compiler error checking bug that accidentally became a language feature, but no, the feature is used in so many places that we cannot afford to fix the original bug. Code that leverages this mechanism tends to be extremely hard to understand even for experts, barely maintainable. Only a few people in your team will be able to figure out how it works. And when you lose these people, you are in big trouble. Another issue with template metaprogramming is that it leads the compiler to do lots of work that's completely unrelated to the work you want to do, like creating instances of type, defining the layout of structs, that sort of stuff. And as a result, if you do lots of metaprogramming via templates, you will eventually get a build that is quite slow and consumes a large amount of RAM, which can be a problem when you use CI nodes with little resources like those GitHub provides by default. So what are your alternatives? Well, you could use preprocessor macros, but these are only good for simple copy and paste situations, and it's actually quite hard to use them correctly due to things like repeated expressions. You could also, if you're that way inclined, parse some compiler-specific functionality that is intended to be a debug output. I've seen some serialization libraries do that. Or you could just throw in the towel and add to your build some kind of external code generator like root, as we use in high-energy physics. But this adds quite a bit of complexity to your build system. Rust has different mechanisms to handle these needs. First, some things that would have to be done via template metaprogramming in C++ can be done with traits and generics in Rust. We also get build scripts, which are more appropriate for situations where you are trying to generate binding to some C code that is found on the user system. And finally, we have a third possibility, which does not exist in C and C++, which is, I would call lexical macros. These differ from the macros that you know in C and C++ because instead of operating on a text stream where basically they copy and paste stuff, they operate on a higher level representation, which is closer to an abstract syntax tree. And as a result, they have a much better trade-off between ergonomics and expressive power. To give you a taste of this, there is a very popular library in Rust called Serde, which can be used to annotate any struct that you have declared so that you get universal serialization and deserialization code. The idea is that you just import the serialized and deserialized implementations from the Serde library. You put some derive serialized, deserialized annotation on your type, and then you can use any library in the Serde family to serialize and deserialize your struct to JSON, CSV, pickle, and so on. No extra code needed. Serde is not the only one to use macros for this purpose. For example, the language provides a built-in macro to generate debug output representation for types, which is why it's very universal. We mentioned build scripts and stuff like that earlier. Let's get to the question of how we build software in these compiled languages. In C and C++, I would argue that the most popular option these days is to use a combination of CMake as a build system and dependency management, and the whole, on Linux at least, using the distribution-specific packages, which means that your build effectively requires different instructions for each and every Linux distribution, first. And second, it also means that you will get wildly varying versions of your dependencies in a way that you do not control. My opinion is that if you don't hate these tools yet, it means that you've not been dealing with them enough. You somehow managed to offload the task to someone else, which is not so nice. The outcome of dependency management being so hard in C++ is that people in the C++ community have quite a high aversion towards code reuse. They will only reuse code if they really, really have to. Like, it would be a huge amount of work to rewrite that code. And this means that in the C++ community, we get a much higher tendency to reinvent the wheel over and over again than in other languages. The way Rust tried to address this is by including a tool called Cargo in its standard toolchain. This tool has two purposes. It serves as a build system. It can orchestrate your build, all the steps needed to produce a binary. But it also serves as a package manager that can be used to fetch dependencies. The thing that's nice about Cargo is that if you're starting out doing a Hello World small project, it's very easy to use. Yet it can scale to much larger projects, like a full web browser, for example. This is what Mozilla tried to build with Servo. And one thing that Cargo managed to do, which CMake and the Linux distributions didn't, is to make dependency management easy. As a consequence, people in the Rust community are much more eager to use external libraries, and then we get a much more lively library ecosystem. Overall, I would argue that C++ has a problem these days, which is that it's a bit drowning in its past. Like even existing practitioners of C++ often don't manage to keep up with the pace of new standard revisions. And more worryingly, in my opinion, even new C++ students are often trained on patterns that most experienced practitioners agree should not be used in new code. Compilers don't help here because they also take years to follow up on new standard revision, and it's very common to be limited in your choice of C++ standard revision because some compiler you want to support does not support this standard revision yet. This is especially the case if you need to cope with some difficult ecosystems like Red Hat or embedded, where it's common to have very, very old software versions around. In general, even if the standard committee tries to overall improve C++ gradually over time, I can't help but think that all new C++ decisions keep being influenced by ghosts from a distant past, like the C preprocessor macros working via copy and paste includes ill-defined primitive types, like when you see a long in a program, you have no idea what size that is. When you see a char, you have no idea what sign that is, and it becomes a portability issue when you write a program on an architecture where these types mean one thing, and then you try to port it to a different architecture where these types mean a different thing. Type literals, in my opinion, were a major mistake in the design of C that C++ inherited. It means that if you want to do a single precision computation, you need to write point F all over again, which is madness. Many defaults, we would argue these days, are a bit wrong, like the fact that switch fall throughs by default, the fact that assignment copies by default, the fact that you need to mark things at const instead of marking them as mutable. And then there are just things that were badly designed in C++, but we still need to live with them today. And I would argue that fortunately Rust actually has an answer to this problem too, which is to basically become C++ future and show C++ how it's done. If you look at C++ 17 from the eye of Rust version 1 practitioner, knowing that Rust version 1 was released 2 years before C++ 17, you can't help but seeing C++ trying hard to catch up, copying and pasting good ideas from the Rust language and standard library, which is fine and all, but try to do some original stuff too, maybe. And you can also can't help notice that some of the copies are not quite right. Like they are very hard to use, and you get people avoiding them actively for this reason. Things like std optional, tuple, structured bindings, class template argument addition, std variants are much harder to use in a C++ context than their equivalent in Rust. C++ 20 more recently has been on a very similar trajectory from the eye of more modern Rust releases. Again, sometimes it manages to copy the Rust features quite well. Other times, well, problems occur, let's say. My conclusion from this would be that there are really 2 good reasons to start a C++ project in 2024. Either that new C++ project is actually part of a larger C++ project that you don't want to rewrite. That's a good reason to write your new module in C++, because interoperating C++ and Rust is actually a bit hard. And the second main reason is that your project relies on some software elements that are a lot more mature in C++ than they are in Rust. Libraries, tools like for GPU computing. I would argue that in any other situation than these two, you should consider the use of Rust. Because these days, the language has become mature enough that it's rarely the limiting factor. Really often, the limiting factor is libraries, and I mean, libraries can be written if their need arises. In exchange for using this less mature ecosystem of libraries, what you will get is a language with much better ergonomics and much better designed libraries. And this means that overall your programs will get less bugs, or bugs at least that get detected earlier by the compiler before they have the time to cause issues. And thus you get more time to add new features and implement performance optimization. Therefore, I would argue that Rust, ironically, is easier these days to learn and has better support from its community and from the tool ecosystem than modern versions of C++. Thanks for your attention. Do you have any questions so far? Please use the Q&A feature. Where is it gone, actually? So I see the question about what do you think about Rust? Sorry, for data science. So here actually the competition is a bit more nuanced. It would be more about Rust versus Python than Rust versus C++. Again, the main issue you would have choosing Rust instead of Python is that you would be using a less mature library ecosystem. You will end up with immature libraries that you need to contribute to, that you need to extend yourself more often. In exchange, what you get compared to Python is a language where it's easier to reach peak performance and where it's easier also to write correct code because you get more compile time type checking, detecting many classes of error. One common approach to try to combine the benefits of Rust and Python for data science is to write Rust code modules that can be called from Python. If you do that, then you get some benefits from Python. On the other hand, the problem is then you pay the price of the function call overhead from Python to Rust and back, which can actually become a limiting factor if your Rust primitive is too fine-grained for Python. So there are limitations to how far you can apply this technique. Are there efforts to address GPUs from Rust? Yes, plenty. First of all, we have many cases. We have a relatively mature ecosystem for addressing GPUs in the traditional way that people would do GPU before things like CUDA existed in C++, things like OpenGL, Vulkan, the web GPU these days. These are quite mature. The problem is, compared to what people have become used to on the C++ side, they remain quite verbose and low level. And therefore, there is a long-standing desire to provide some high-level primitives, but first we need to get the basics covered well. And here there are some disagreement on the approach. Some people want to leverage the Clang features for GPU offload, or the LLVM features for GPU offload. Some people want to have Rust code that transpiles to SPIR-V, which you can then use from Vulkan. So this is a bit in flux at the moment. Can we consider C++ a prototyping language before writing a proper Rust implementation? Well, I don't know. I would argue that one nice property of a prototyping language is to be able to quickly iterate without getting lost in the specifics of the programming language you're using. Some people argue that static type systems are not suitable for prototyping for this reason. This I would personally disagree with, but I understand why people would think that way. But in any case, C++, in my opinion at least, is a much harder language to use than Rust. So I wouldn't want to use it for a prototype. Instead, I would probably go the other direction actually and write Rust prototypes for my C++ programs. What does more consistent and reliable libraries mean? How are these libraries built, tested? Yeah, I have no idea what happened to the Q&A. I see it. I managed to open it again. So I don't know what happened, but if you go to the plus section, now you have it. So then what I will do is I will probably move a bit to the Q&A section and then go back to the chat, but please use it once you found it. In my Zoom interface, you go to the plus section at the bottom, and then you can have it in the menu. About finite binaries performance of Rust code versus Fortran C++. Well, as you'll see, we can get to a similar place. Which is to say that given enough effort, we can get pretty much perfect assembly similar to the one that the assembly expert would have written by hand. How easy it is to use the Rust foreign function interface to use major C++ libraries like Eigen and Cirrus? Well, one problem here is that Rust has a very solid foreign function interface for C, because when you compile a C library, then in the compiled binary, you get a list of all symbols available in this library. And then you can call any of these symbols without calling the C compiler again for help. This is not true in C++. Like if you use Eigen, for example, you have lots of templates. And in order to use a template from Rust, what you would have to do would be to somehow translate the template declaration to some kind of limited Rust declaration. Then the Rust compiler would have to see this declaration, notice that it's not a native template, call into the C++ compiler so that it generates the appropriate code, then generate some kind of Rust binding to this generated C++ code from the template, and finally bind that on the Rust side. That's a lot more difficult, and that's why we don't have it yet. Could you talk more about the downsides you see of Julia? I'm curious if there are any use cases where you would choose to use it over Rust. So, in my opinion, the thing with Julia is that it's a bit like NumPy in Python. They try to have something that feels very high level and dynamic like Python by default, but where a subset of the possible code paths is optimized very well. Like basically, if you write C or Fortran code in Julia syntax, it's very efficient. That's a bit of an issue because it means that it's very easy, if you're not careful, to accidentally introduce in code that's supposed to be high performance some constructs that cannot be implemented efficiently in Julia. And then your performance drops to a hat. Like, for example, you can have a function that performs division of some numerator by a denominator, and then you realize that, oh yeah, but the denominator may be 0. So then you add a special return path where in that case, okay, you return 0, that's wrong, but that's fine. And the problem is, if you write the literal 0, then you get a type unstable function in Julia, which can either return values of type float or of type int, because the literal 0 is of type int. And then what happens is that your function may return values of different types, so you get boxing, memory allocation, and it gets slow. When would I use Julia anyway? In cases where people do not have the luxury to spend time learning Rust. Rust is quite a complicated language to learn, and for some customers, like researchers, colleagues, whose main business is to do physics, not programming, the complexity of Rust can be too much. And there, I think Julia may have its chance. I'm relying on the Eigen library for linear algebra. Does Rust have any major linear algebra libraries? We get some. We have an algebra, and the array has a bit of algebra to it. We get also these days something called FAIR. They are a bit younger than the ones on the C++ side. So probably they would have more limitations, but whether they are good enough for your use case or not, I would just check the documentation and leave you decide. Maybe let's go back a bit to the ones in the chat because I'm getting to the point where the ones in the Q&A section are getting ahead of those of the chat. What does more consistent and reliable libraries mean? How are these libraries built, tested? Well, the test practices in Rust are relatively similar to those you would use in C++. You have unit test, integration test. You can also get some property-based testing. It's very common to have continuous integration with linters, runtime analysis for some purposes as well. The main difference is that by virtue of having a better designed standard library and some key players of the library ecosystem also spending a lot of time on their API design, there are many more errors that are prevented at compile time in Rust, or at least detected at runtime, than there are in C++. Also, many of the big players of the Rust ecosystem are old, experienced C++ programmers who got years to learn the hard way all the things that can go wrong in API design in C++, and then they apply this knowledge to REST API design to produce better APIs that have less problems. So interoperability story between C++ and Rust, I think I have covered that. Basically, the C subset of C++ is easy to interoperate. As soon as templates are involved, it gets trickier because then you need to call into a C++ compiler to generate code, and people are not yet ready to do that, even if there is some desire to. What is the cost of vector bound checking in Rust? Does the Rust compiler execute format verification? In what sense is cargo better than CMake fetch content? Many questions. I'll start with the first one, maybe. So this one was also posted to the Q&A. Okay. Very well, then I go back to the Q&A section. So this answer I covered. What is the cost of vector bound checking? So if you basically take your C++ loop, translate it to a Rust loop that does indexing within the same squared bracket operators for the input arrays, you may get in trouble because of this. The reason Rust practitioners do not consider it that big of a problem in practice is twofold. First of all, Rust has a very well-developed iterator ecosystem. It's more sophisticated than the iterators we get in C++, classic C++. It's more akin to the ranges of C++20, which were largely inspired by Rust iterators. And because they have a better design where the iterator knows where the end of the iteration is, it means that you can take Rust iterators and get a lot more mileage out of them. You can do more complex things like window iterations, stencil computations with iterators in Rust. Stuff you wouldn't do in C++. You can also easily transform iterators to adapt them to your needs. And iterators themselves are implemented using the unsafe subset of Rust, so they have no bound checking overhead. Does the Rust compiler execute formal verification as FramaC? It's less sophisticated than a typical formal proof engine, like Z3, FramaC, and so on. But it can prove some properties like type safety, memory safety, and thread safety. And there are some ongoing more experimental efforts towards integrating full theorem provers in Rust, which would allow you to specify your own precondition, postcondition, invariant, and get formal proofs at compile time. There are many examples. We can talk more about this later. I can send you some links. In what sense is cargo better than CMake fetch content? So there are many things that are problematic about CMake fetch content. First of all, when you have a dependency that uses fetch content, it is that dependency that chooses which version of its transitive dependency it uses. You cannot, for example, make sure that all your dependencies are using the same version of eigen, FFTW, and so on. And this means that you can easily end up trying to link different versions of these libraries with each other, which will result in something that's technically undefined behavior, and in practical terms will lead to very weird linker errors or very puzzling runtime behavior. Cargo, on the other hand, correctly manages the problem of trying to pick a unified version of dependencies. And the Rust linking rules are designed in such a way that if you have to, I would not recommend it, but if you have to, it's also possible to link against multiple versions of a dependency without getting too many issues. Basically, the two main issues is that you cannot pass values from one version of library to another, and the global variables are duplicated, which can also cause some kinds of trouble. Downsides of pure C, well, as soon as you want to do some more sophisticated abstractions, like, matrix types, linear algebra, C becomes extremely verbose. And it's easy to get code that is more basically composed of function names than mathematics. That's why we got languages with operator overloading, and I wouldn't give up on it myself. Besides that, some of the drawbacks of C++ are common with C. C also has undefined behavior everywhere. C++ inherited most of it from C. Yeah, we could go more about this, but basically it boils down to having a more sophisticated type system that can scale to more use cases without becoming painful and verbose. So the next question was answered by someone else, so I will not comment more on it. Yeah, according to Google, it takes about 1.5 to 2 years to get the same level of productivity in Rust as in C++. In terms of, more I would say the 70% productivity, I would say that in a few months to a year, you can already be pretty proficient in Rust. But you will still hit some roadblocks with some specific areas of the language, like lifetimes, for example. These take a bit more time to learn. You mentioned going through the CADI link to instantiated C++ templated code. How do you deal with heavy use of polymorphism? Do you use automated tools? As I mentioned, there are many ways to do polymorphism in C++. You have at least in the sense that, you have one operation and you can apply it to many different types. You can do it via overloading. You can do it via object-oriented interface. You can do it via methods that have default parameters. Depending on the specific type of polymorphism that you're dealing with, the answer will be different. For templates, as I mentioned, it's a big unsolved issue, basically. So for templates, yeah, basically right now we have tools like CXX that can provide, the useful 10% of templates. Like, for example, you can have std string, std vector, interoperability, but general templates right now are a bit of a pain. Basically, you need to write a sieve wrapper around them for all instantiation you need, and yeah, more automation is really desired. And probably the C++ interoperability initiative that started this year will be about making this easier. There is a significant appeal in interactive Python REPL for exploratory analysis. Is there anything you would recommend for the Rust clan to avoid compilation loops every time I change the code? So yeah, as someone mentioned already, you can use scripting languages first. You can bind to them. There is even a library, I don't remember how it's called, which allows you to just write Python inline inside of your Rust. You can, it's more difficult, but you can also use stuff based on dynamically loadable libraries. The Bevy game engine has taken this approach quite far and could be an example to study. And finally, you can use Rust itself inside of a REPL using a project called EVCXR Rust. However, the language was not designed for fast iteration, and you may still feel that the compilation times are a bit too much for interactive use. Finally, of course, as I mentioned earlier, you can keep using Python and offload your most compute-intensive parts to Rust. Sorry, this is covered in the later part. Are there any distributed memory API usable with Rust, MPI, and so on? If yes, what about high-performance interconnects with like Mellanox? Does it need to be unsafe? This is a part which myself I have not studied that much yet. However, I know that there is an MPI binding, as someone mentioned. That would be the main entry point I would start from. I can also later provide you with some pointers to libraries that try to provide higher level approaches closer to having distributed iterators where the iterations are automatically distributed over many machines, but this is in the earlier research stages at the moment. You compared here C++ to Rust. What do you think about Zig? So Zig, I would say, is easier to compare to C than to, it's more of a competition to C than to Rust. It's one of these languages, again, where you don't have operator overloading, destructors, many conveniences, and the idea is more to have very tight low-level control and to be very explicit about everything, passing iterators every time you allocate memory so that you can customize the, sorry, not iterators, allocators anytime you call code that may allocate memory so that you can control the allocation behavior. I would say it's an interesting research direction, but yeah, someone mentioned it's a bit young also. But for scientific computing, I would personally not use it, but to each his own. Rust Python Rust binding is, according to the word, inefficient because of the overhead of calling Rust Python back and forth. What do you think about Python, where this overhead is already more or less diminished, and you can in fact combine prose and Python, prose and C with, and more or less get rid of disadvantages of both? Well, in my opinion, Python is effectively a bit of a different language than Python, right? As soon as you start using Python, you must constantly bear in mind what is the subset of Python that Python knows how to compile efficiently. You must bear in mind what type annotations you need to add to your Python code so that it can then be compiled without falling into PyObject calls. In my opinion, writing Python code is a bit like writing C in Python syntax. And if I wanted to do that, I would be using NIM, not Python, right? So it looks like there are less questions. So maybe we can get started on the more practical part. Thanks everyone for your insightful questions, by the way. Much appreciated. So during registration, you may have received some instructions about how you should set up your computer for Rust development during this tutorial. I hope you got time to follow them. If not, you can find them on the timetable of the Indico page at the top near the registration link at the bottom of the summary. I can share my screen to show that. Yes. So there, you get, you start from here, for example, at the top level page. I don't know why my internet is so slow today. You have it right on the side menu. or you have it in the full program here as well. So the idea here is that because you come from many different places, you may need to use several different environment setup instructions. So I tried to cover all the common cases. Please tell me if anything goes wrong. You can use the Q&A for that. It will be more structured than the chat, I believe, as soon as several people start talking. Once you've done that, then you can go to the top of the agenda for today, Monday, and you get a practical work link. And then you get some extra instructions to get the latest version of the exercise source code. I actually didn't need to update it after all, so if you downloaded it before, it's okay. You can keep the copy you downloaded at that time. And then you will get a tutorial that's written in a relatively verbose style. So the idea here is that you are many participants and you come from many different horizons. Some people are already quite familiar with Rust and want to get more in touch with the numerical side. Some people are more familiar with numerical computing and want to become more familiar with the Rust side. Some people are not very experienced in either, but just curious, and depending on where you come from, some parts of what I'm saying will be easier to you and you will move faster in the practical work. And some parts you will need to spend more time. So the idea to have this relatively verbose style is that you can follow at your own pace, spend more time on the parts that are difficult to you. And we will reconvene from time to time and discuss the parts that were difficult for you to understand. Obviously, I can also answer questions live as needed. So here the idea is that we will start from the very basics of Rust, hello world, variable declaration, and we will get all the way to how we manage multidimensional arrays with Rust. We will not probably have the time to cover all of this today. The intent is to cover it basically from today to early tomorrow. And then we will move to a more challenging problem, a bit more sophisticated in terms of mathematics. And you will see how Rust scales to this kind of problem size, let's say. Any other questions so far? If not, let's get started. Oh, that's bad. Let's see what's going on. Zoom, breaking, copy and paste since forever. Ah, yes, I know why that happened. Anyway, you don't need to see my screen for this, but I will resolve this one. I know what's going on. And for context, this is what happens when you move files inside of a directory in a web page and you forget to update the links. So once the next CI job finishes, you should get a working link to the exercises which will resolve that issue. Can we use Cargo to directly handle the Hello World template and REPL process? I'm not sure if I fully understand this question. Yeah, about the VS Code extension for coding in Rust, yeah, Rust Analyzer would be the one. So yeah, but by the way, someone told me via private message that for now, this link works, but it will soon stop working. So, but in a short while, it will be that instead. So the way it should be. So yeah, for the so for the question from Nikki, can we use the VS Code dev containers extension to interact with the exercises container? I think you might be able to. On the other hand, the whole idea of this container is to provide you with a VS Code that's pre-set up and just works. If you try connecting an external VS Code to the container, then you will need to set up your VS Code to get the same level of comfort that you would have inside of the container. In that case, it might be easier to just do a local setup. So yes, regarding the if a news variable is intentional, please prefix it with an underscore. Is it a classic Rust warning? Indeed it is. The idea is that, you know, in C and C++, you also have it, in Part1 as well. When you define variables and you don't use them, effectively what you're doing, or at least what your code is attempting to do, is to execute kind of useless code, right? Generating this value and you do nothing with it. Sometimes, however, you do need, for more complicated reason, to define values that have no apparent use from a simple, you know, data flow analysis point of view. But these variables are actually used to implement some kind of scope guard. Like, you know, in Rust, when you lock a mutex, for example, you get a mutex guard, which is a special type that allows you to access the data behind the mutex for as long as it's alive. You may sometimes want to lock the mutex without accessing the data, just, you know, to slow down other threads. That's a bit of an advanced use, but whatnot. And then you will want to have this lock guard without using it. So yeah, it's a bit of a more advanced use, but the underscore syntax does have its uses. In general, though, when you see that, the usual answer is, well, either you have created a variable and you forgot to use it, or you accidentally used a different one, and you should either delete the declaration or fix the usage point. And yeah, Michal, I don't fully understand your question, so you will need to explain it a bit more for me to answer. So Patrick, to execute the basic examples in the tutorial, you have multiple options actually, but you will not get all of them for the entire duration of the course. But first of all, inside of the course, you have several examples of Rust code. And if you hover them with your mouse, you will see that actually there's a little button that appears here. one of these buttons allows you to copy and paste code. This can be used, for example, to take examples, copy them to your code editor, try to compile them, and so on. That's one thing. Another thing you can do, however, is to use this button to execute the examples on a virtual machine. So for all easy examples that have no dependencies in the course, you can just get the output directly like that. Now, when we get to more complicated examples, what you will get is that at some point I will have suppressed this possibility because the relevant dependencies are not installed on the VMs that back this in the cloud. So the way I propose to use it is to follow the environmental setup instructions that I have given you in the first section of the tutorial. And then followed by this part where you update the source code. And this actually I see I will need to update as well. I will do that in a minute. And once you've done that, you should have access to an environment where you can build and run code by just going to the directory where the exercise material is and running that. I don't know if that fully answers your question. And yes, as someone points out, this play button is unfortunately not perfectly reliable, but yeah. That's unfortunately an infrastructure that I do not fully control. If you get that error message, playground communication timeout, you can just rerun it and it will succeed after a while. It's just that the underlying server is a bit overloaded. So there are quite a few that I should take care of. Where do I start? I did not get any reply from Patrick on whether my explanation was good enough. Yes, you replied in different question. Okay. But in any case, yeah, if you would like, run a toy project to past code. it possible to somehow get Vim movements in the browser VS Code? I have no idea, actually. Maybe you can install a plugin for that, but the command for this may be a bit ugly. I can tell you how extensions are set up from the command line, and you can try that. And if that doesn't work, maybe try a local environment so that you can get, the VS Code set up the way you like it. Yes, indeed. As Ashwin points out, I actually put a hello world example already in the exercises source code, and you can use it to check that it's working as expected. I eventually replaced it in the instructions with some more extensive checks, but you can still run this check as well. Okay, Devan, I need to check what's going on at some point. It's a bit surprising to me that you get these HWLock issues because I didn't get them when I tried the instructions on Devana. So I need to see what changed on the Devana side since then. Maybe also Joseph can help you. He's the one managing the Devana machines. In any case, so I need to fix my exercises link because right now I fixed it, but not in every place, which will cause problem later on. Yep. All right. Maybe let's take a bit of a tour of the setup instructions together as well. So right now, the way this is set up, I give you 3 main ways to set up your code editing environment. The first one, which is not available to all of you, is if you got access to the DAY1 Computing Center, then I advise that you set up SSH login, make yourself at home with SSH. And then once you get something that's nice and comfy for editing code, you use this particular module loading command to load the environment modules that we use. If you do not want to type them over and over again in each DAY1 shell, you can put them in your user profile. And then you should get a shell in which most comments from the coursework. I see in the discussion that there are some things that don't work. And the main thing to keep in mind when you're using DAY1 is that it's okay to compile code and run simple examples directly on the login nodes. But as soon as you want to do something a bit more expensive or that requires a cleaner system, like doing micro benchmarks, you will really want to use the Slurm workload scheduler. And this you can do here. There is a quick introduction to Slurm that you can use to this end. So again, for DAY1, make sure you can connect to the web interface. Use it to register your SSH key. Here are a couple of tricks that you can do to make future SSH login easier and also to edit files more easily. And then you use this to set up the right software environment. And normally after that, every command should work. And just be careful of using Slurm when you need to. Second option. If you are using a machine that is based on native Linux. And by native Linux, I mean, you are not like running Docker on Windows and Mac OS, which involves running a hidden Linux virtual machine. This will cause problems, unfortunately. Then one thing you can use is to use containers, which come with a prepackaged build environment with all the dependencies we are going to need for the course. And also, one of the containers contains a code editor. So then, you can just get a Rust editing environment in your web browser that can be used right away. Unfortunately, containers can be a bit of a pain to set up. So first, you should use one of Docker Engine or Podman. And that's the two I have tested the containers with. More precisely, I have also tested it with Aptainer, and I know it doesn't work because the way Aptainer manages user accounts is completely incompatible with the way this container is built. Then once you have a working Docker or Podman, as usual, you need to get the exercises source code. And here the idea will be to start the container and mount the exercise source code as a directory inside the container. And when you do that, this allows you to be able to edit files from your local machines and see them reflected in the container. But also, it also means that anything you do in the container will still be on your hard drive later on when you stop the container. Whereas normally, when you stop a container, all files inside of it are lost. Unfortunately, there's a bit more setup involved, but in any case, once you get it working, then you can just open a terminal in the Visual Studio Code editor, go to the exercise directory, which you should be in already, and that container is working. I also provide a lighter weight container where there is only a development environment and no text editor. This is intended for people who want to use their own text editor, like, you know, they like Emacs, they like Vim, I don't judge. And then what you can do is you can start from this lighter weight container and install what you need on top of it. This, I think, should be a better path for those people who wanted to use dev containers in VS Code. Finally, I also provide a local installation option. Normally, that's the one that's most risky because it depends on what Linux distribution you're using, what you have installed before, what locally installed software you have in your path, and so on. So you can expect more problems with these instructions. But on the other hand, if you get them to work, it means that after that, you don't get the extra complications of SSH or containers. You just get, you know, local software on your machine running right away. So here the goal is to set up a development environment, a code editor that can edit Rust, and you're good to go. And I provide instructions for Linux, where you have the list of packages for all common distribution families, Rust installation, some HDA5 to PNG renderer, and tests for your environment. You have also instructions for macOS and Windows, which work in a similar way, except on Windows it's more complicated because Windows development is more complicated. I will now proceed to try to look into the various things that have been said in the question and answer panel. So some people get issues accessing Devana. I see that Michal is working on this one. So I will leave him this part unless it's somehow specific to my setup, and then we can discuss more. So someone gets a failure to install the data2pix utility on old versions of Ubuntu. I'm not sure actually if it's, someone says it might be a Rust version issue. I'm not sure. I suspect it might be an HDA5 version issue where somehow the Ubuntu 20 version of HDA5 does not have the right method. That could be that. If that's the case, then it's possible to fix it by tweaking the build configuration to make the HDA5 metno dependency build its own HDA5, but that will be a bit more work. I'll just check if it has this option to do its own build first. Yeah, you can point it using some environment variable to your own build of HDA5. So assuming that's the issue, where again, I'm not sure of that. One way you can fix it is by building a more recent release of HDA5 and pointing your, using this HDA5 dir environment variable to point your builds to use your more recent build of HDA5 rather than the one that your distribution provides. And if you do that, you might get something working. But then you need to be careful to also set LD library path or so on, so that you keep using the same version of HDA5. So it's a bit of a brittle setup. In any case, if worst comes to worst, using this utility is optional and it's just a convenience for visualizing what you're doing. But at the cost of not having a that picture, you can also just, not use it and hope that your code is correct. Playing around with vec. So Mathieu, there with when you use vec in Rust, which works like std vector in C++, yeah, Mossa just replied. It does not mean, you have to bear in mind the nuance between two different things. One is the length of the vector and one is the capacity. The idea is that you can have more allocated storage than the current length of your vector. And this is used so that if you keep pushing data in a vector over and over again with push, then you will not allocate new storage and move the existing data every time you push. Instead, the implementations of these containers use an exponential allocation strategy where every time you run out of storage, you allocate twice as much storage. And this means that overall you get amortized constant time insertion instead of paying a linear time operation to allocate and copy on every element insertion. I hope this clarifies it. Build not dot profile is not executed on login on Devana. It's the first time I see a shell that behaves that way. If so, then you can try .bash profile. Which I think is sourced by bash always. So yeah, the next question, the answer is almost right. Not quite, but good enough. It's wrapping add, not wrapped add. So Peter asks about how to start in Visual Studio 2022 in Windows 10. So assuming you did all the remainder of the environment setup, which is listed in environment setup, local installation Windows, then you should be able to download and extract the exercises source code. You should be able then to open this source code, the extraction of the archive will create a directory called exercises. You should be able to open this directory with Visual Studio. And then you can edit files, like you would with any code editor. And if you keep a terminal nearby, you can also go to this directory in your terminal and do cargo commands. It's probably possible to tell Visual Studio itself how to, when you click the build button, do the cargo build and so on. This I'm not super familiar about, so I will leave you to search for tutorials on that. Does that answer the question? So waiting for the reply of Peter. Maybe I will close the question for now and you can open another one if it's not clear enough. So apparently the cargo examples command does not work. Yes, that's because you need to install an extra utility for that, which I unfortunately forgot to include in my builds, but you can install it like so. And I need to remember to fix that in the next release. Because of cargo, those Rust have a smaller standard library than that of C++. I would say they are maybe about the same size. They just put focus in different area. Like for example, the C++ standard library does not feature some collections that Rust has, like a priority queue or binary B-tree for ordered collections. On the other hand, it does feature things like parallel algorithms, which in Rust you do not need because with traits you are able to implement that in third-party library, and that's exactly what Rayon does. And with Cargo, it's very easy to install that library. So yeah, basically, I would say the standard libraries of Rust and C++ are of similar size, but put their effort in different places. Oh, great. Failing builds. Well, let's start. Let's try to restart them and see what happens. Do we have BF16 proposals in Rust yet? This I don't know actually. Anyway, you don't need that. So today we have BF16 type in the half library, but I believe this one currently relies on software emulation and not native execution. Is that correct? Uh, No, actually, the crate does try to run them in hardware. So and that crate has support for x86 and IArch64. As for language inclusion, I don't know. So for the boxcar exercise, which is in which exercise? Let me see.
Exercise 3 with looping.
Okay, perfect. Then let's look into it. How did I write that one? So you can write a function if you want, or you can just write an iterator pipeline inline. Or you can write an explicit loop and start by allocating a vector with certain capacity and pushing elements into it and so on. It's up to you.
I guess the iterator pipeline would be ideal to have it inlined, but I wonder if it's the level that we are ready to do at the moment.
Yeah, maybe at that exercise it's a bit early, so maybe we'll want a simpler version. But yeah, you do have already studied Windows, so that could be used, maybe.
But does it require a lambda to pipeline it?
Yes, indeed. So that's then you would have to do it with a loop.
Mm-hmm.
Because we have not seen lambdas yet. They are in the next chapter. So where with a loop, you could set up some storage with some capacity, start looping over the windows of the input, and then compute your averages and add them to the output array.
Okay, thanks.
That would work. Weiming, sorry, I had to step out for a little bit. Could someone let me know which sections we are currently on and what I'm supposed to do? Thank you so much. I have set up my environment, downloaded the example source code. So the general idea of this practical work is that it's mostly self-paced, but I propose that from time to time, we gather around and do a bit of a rallying point where I go over what we did and go through some steps with you. So then I would start from the first steps chapter. If you've not done it already, go through it, the numbers chapter, loops and array and so on. I would actually propose, if everyone else is fine with that, that we do a bit of a break now, because I don't know for you, but in my case, I've been talking for 2 hours now, so I'm getting a little bit tired. And we get back to this in a quarter of an hour, let's say, and then 20 minutes. And then I just go through the first chapters with you.